Hey folks, welcome to this episode on pressure. So, when you're given a bottle of any kind of gas and you're asked to find out how many particles of gas there are, you have to take into account a couple of things. Now, first of all, you have to see how big the bottle is. Now, in this case, it says a liter bottle of air, so you know what the volume that the gas can take up. The question is how much of that volume is actually being taken up by that gas? Well, that depends on a number of things. Number one is the temperature. So when we look at the temperature, let's look at these two bottles that we have over here. Now here we have a normal bottle and the gases are kind of static looking. No, that they're not, they're constantly moving, but they haven't expanded into this balloon that's attached to the bottle. Now, one thing to say about the volume is that this is a glass bottle, so the volume is actually pretty constant. If it didn't have this balloon, it's kind of capped off here, that volume wouldn't expand. However, the volume that is we see here is expandable because it has a balloon attached to it. Now you can see in the second bottle, when we turn the heat on, this water starts getting warmer and that transfers heat into the gas particles, causing the gas particles to move a little bit faster. Remember, going back, as we increase our temperature, we're also increasing our kinetic energy. So our kinetic energy in the second one is increased and it kind of moves these gas particles into this balloon over here. Now, let's say we actually infused, we took a syringe, we stuck it in there, and we infused a whole bunch of other gas particles in there. Well, what does that say about the volume that this would occupy? As we saw before, more of these gas particles going in means it'll probably take up more volume as well. But the last thing is pressure, which is what we're going to be talking about today. So pressure and force, what's going on with these things? Well, let's think about a balloon. And I'm sure that most of you have had a balloon before. You've put air inside the balloon and you saw it expand. It's pretty fun. Now, when we look at a balloon, how does it actually expand? Well, if you think about it, you're putting air into this balloon. And what air is basically just a whole bunch of gas particles, carbon dioxide, oxygen, argon, nitrogen. And as you're blowing into the balloon, you're putting all these particles inside of the balloon. You can see here, in this case, it's helium. You're not expelling helium, but we're otherwise introducing it in through maybe like a nozzle of a tank. So we're adding helium particles or molecules, atoms into here. Excuse me, not molecules, atoms. And these helium atoms are moving around and they're bouncing off one another and they're bouncing off the insides of the walls. Now, as they bounce off the insides of the walls, they're actually pushing out this balloon. And that one little spot, this balloon is going to be moving outwards this way. Now, as this molecule moves over here, it's going to push out to the side of the balloon and so on and so forth. And what you're going to start seeing is that as you introduce more of these helium atoms into this balloon, or air if you're blowing it up, there's going to be more particles inside of the balloon, and those more particles are going to start pushing more and more onto the outside of the balloon. Now, what those particles are doing is they're exhibiting a force on a specific area of the balloon. Now, as we're going to start seeing, force over area is going to be equal to pressure. So as we saw, this pressure is equal to the force over the area that the force is applied. So if we were kind of poked with a pencil, let's say there was 5 newtons of force, and we were poked with a pencil, you can see that the area that it kind of contacts is much larger than if we were poked by a needle. Now let's say we still used 5 newtons of force, but we were poked with a needle that has a smaller diameter and therefore takes up less area. Now, which one would cause the greater pressure, the pencil or the syringe or the needle? In this case, you'd be right if you said the syringe, because even though the same force is applied, the area that it's being applied onto is a lot smaller when we're talking about the needle. And therefore, if the area is smaller, our numerator is smaller, that means our pressure is going to be bigger. So how does this relate with gases? Well, anytime there's gases inside of a container, those gases hit the inside walls of the container. And when they do, they hit with a certain amount of force over a specific amount of area. And so when they do, they're creating pressure of that wall of the container. Now, usually these things are measured in newtons, but we also do have a lot of different other units depending on the application. The ones that we use mostly is kilopascals or kPa, which is the standard that we see here. The standard unit is actually pascals, but a lot of you may also use atmospheres. Now, you've probably seen things like PSI before or bar, but we stick with kilopascals for our calculations, because we are going to be using something called the constant, and that is all based on kilopascals or atmospheres. When we look at pressure, we can look at this ballerina who's doing a whole bunch of dance moves, and in each situation, she's applying 500 newtons of force in the downward direction. The difference, however, is how that force is being distributed. In the first one, she's actually having these flat feet, and the bottoms of her feet are actually distributing that force over a larger amount of area. Now, if pressure is equal to force over area, and our area is a lot bigger, then that means our pressure is going to be a lot smaller. When we compare it to something like over here, she's pushing down 500 newtons of force, but the area that she's doing it in is a lot smaller. So the same amount of force, but a smaller amount of area, will mean that you're going to have a much larger pressure. Now, how was this really discovered? There was an individual called Torricelli who filled a glass tube with mercury and inverted it into a reservoir filled with mercury. So this whole glass tube was full of mercury all the way to the top. Inverted it, put into the reservoir over here, ensuring that no gas kind of gets in. Now, what he discovered was that when this tube was inverted, some of this mercury sank down. It sank down to a level, or if you put graduations on it, sunk down to a level of 760 millimeters of the mercury that you put in. Now, why did it actually sink down? Well, remember that it's a heavy metal, and it's wanting to get out of this tube. Now, if this whole area around here was a vacuum, meaning there's no particles, what would actually happen was that this mercury would actually sink down exactly to the same level of the reservoir. So as this would move in, the reservoir would get higher, and the amount of mercury in the tube and the reservoir would be the same. However, that's not what he saw. He saw that it stayed at this level, which means that there would actually have to be something on the outside pushing down on this reservoir to keep it at this level. And what he discovered was that this was called the atmospheric pressure. So the atmosphere is really filled up with a whole bunch of gases like carbon dioxide, nitrogen, oxygen, argon, for example. And all of these things actually put a pressure onto various things. In this case, this thing called a barometer, which just measures the atmospheric pressure. So all these gas molecules that are in here are actually pushing down on the reservoir of mercury, causing this to be at this level. Now, how much? Well, they define this. How much pressure is defined as 760 millimeters of mercury. Now, that's also equating to 760 torr, which is another unit of pressure, but most commonly we call this 1 atmosphere. Now, what happened if this atmospheric pressure would increase, so we had more pressure? Well, it would push down farther in this reservoir, and this value of the millimeters of mercury would be increased. If there was less atmospheric pressure, this volume would go down, and so our millimeters of mercury, or our pressure, would also decrease. Now, scientists found it useful to do these calculations in a set of standard conditions, and they call this standard temperature and pressure, or standard ambient temperature and pressure. Very slightly different. It all depends on the conditions of where the reactions are happening or the calculations are being done. So when we're looking at standard temperature and pressure, this is really the standard. It's 0 degrees Celsius, or 1 atmosphere, or just a little bit under an atmosphere, which we kind of equate to 101.3 kilopascals. Now, 273 K is another unit of temperature, and we'll talk about that in a bit. It's called the kelvins, and it's very simply converted from Celsius to Kelvin by just adding 273. However, a lot of chemists and biochemists and biologists didn't really want to work in 0 degree conditions, so they equated this to 25 degrees Celsius, which is room temperature, and they call it standard ambient temperature and pressure. So sometimes you'll see STP or SATP. These are the conditions at which those calculations or the measurements were made. Now, to move from one form of pressure into another, we can use this little graph to figure out how to get there. So, for example, if we start off with millimeters of mercury, or torr, which are both 760, we can divide by 760 to get to an atmosphere. And you can see that we can branch off from a lot of these other forms of pressure from this atmosphere. So a lot of the practice is to get into atmosphere and then we move away. So here we have pounds per square inch, or psi. We have bars, we have kilopascals and pascals, which is the standard unit, millimeters of mercury, or torr, which are the same values, and here we have newtons. So again, that's for pressure. If we wanted to convert temperature, we need to do a very simple process where we go from Kelvin to Celsius by subtracting 273, or Celsius to Kelvin by adding 273. Now, why do we go with Kelvin? Well, Kelvin, 0 degrees Kelvin, is actually what we call absolute zero. Nothing can be colder, and that's where all motion stops because all the energy from substances is gone. Entropy is zero. Entropy, if you're not familiar, is disorder. So at 0, there's no kinetic energy. All the molecules are not moving, so they're very, very close together, and entropy is very, very small. So what we use is we use kelvins for all of our calculations in the gases. So let's just do a little conversion practice. Here we have a storm that's approaching Toronto. The mercury barometer shows a fall in pressure to 723 millimeters of mercury. What is the pressure in kilopascals? So the first thing that we want to do is highlight what we're going to be going from. So we're going to go from millimeters of mercury, and we're going to go to atmospheres, and then we're going to go to kilopascals. So to get from millimeters of mercury to atmospheres, we take 723 millimeters of mercury, and we multiply it by the ratio. So we have 1 atmosphere is equal to 760 millimeters of mercury. And so what we do is we get 0.951316 atmospheres. And then again, the relationship between atmospheres and kilopascals is that we have 101.3 kilopascals for 1 atmosphere. In this case, our units cancel out just like they did over here. And we get our answer. Our answer has to be in 3 significant digits, so we have 96.4 kilopascals. And that is our final answer. 3 significant digits because we had 3 significant digits there. Now here, the second question says, now oxygen technician knows that we have that at 296.3 Kelvin, the pounds per square inch of an oxygen tank is 2,670 psi. What is the temperature in degrees Celsius? So to get from degrees Celsius to Kelvin, we add 273. So here we're given Kelvin. All we have to do is take Kelvin minus 273, and we'll get degrees Celsius. So if we take 296.3 Kelvin and subtract 273 from it, what we get is 23.3 degrees Celsius. So try your hand at converting some pressure and temperatures. So pause the video. Once you're ready, we'll come back with the answers. So go ahead and pause the video now. So here are your answers. For the first one, we had to go from psi to atmosphere to kilopascals to pascals. That's a little bit of a stretch. So we multiplied by all the ratios here, and our final answer was 5.51 times 10 to the 4 pascals. When we're looking at breaking ribs, we need to apply a force of 3.3 kilopascals. Again, here we have 2 significant digits, so our final answer is in 2 significant digits. And going from Celsius to Kelvin, we need to add 273, so we get 232 Kelvin. Thanks very much for watching. See you soon.